open up the panel. First up, we have Stephen Bach, who has given us a talk on using knowledge graphs to learn about neighbors. He is an assistant professor at the computer science department at Brown University. His current research, as we've seen before, is on weakly supervised machine learning. And his interests also span across statistical relational learning and information extraction. Thank you. Stephen, could you take the place?
Sure. Can you hear me okay?
Yeah, you're good.
So I'll try to be brief, famous last words, but I think the things that I'm most excited about these days is kind of this progression along the types of graphs that I've been working on over the, since grad school days. So you mentioned in the intro statistical relational learning. When I first started working with graphs, I was thinking about information graphs and graphs of data, like, for example, protein-protein interaction networks or social networks, things that we might observe in nature. And so one of the things that we can sort of think about different types of graphs almost like on a spectrum, where these data graphs are maybe the most concrete. And then you get to maybe more abstract graphs like knowledge graphs. And even there you have kind of a bit of a spectrum. So for example, something like the knowledge graph, the Google knowledge graph is relatively concrete still because it's focused on entities. So if you want to know who the head of state of a particular country is, it's a great knowledge graph for that. But lately, as I talked about in my talk, some of the things that I'm most interested in are kind of the really most abstract graphs like common sense knowledge graphs, because I believe they give a way to capture a lot of what's hard or tricky to model about the world in the way that has led us all to like graphs in the first place, that they have kind of this mix of explicit structure and flexibility. So, this work is just starting. As I talked about, what we're trying to do is let people describe concepts in terms of graphs, and then map them to classifiers, tools that actually are useful for specific tasks. And ultimately what our goal is to make graphs a kind of programming language for machine learning in terms of describing our work, or describing the work that we want them to do. And so this is based on some of the things that we've seen in weakly supervised machine learning, where subject matter experts need a way to kind of communicate what it is that they want to do in a way that's more efficient than hand labeling data. And so, what I'm really excited about is continuing to try to push in that direction. And it's just a very interesting mix of multiple areas of machine learning, but particularly as it relates to graphs. What are the right kinds of structures for describing the inherent messiness in concepts in the world? So that's something that we're excited to continue.
Thank you. That's very exciting. Next up, we have Ginestra Bianconi. She has given us a great, excuse me. She's given a great talk on information theory of networks. She's currently a professor in School of Mathematical Sciences, Queen Mary University of London. She has various interests within statistical mechanics of networks, specifically multi-layer networks, network topology, quantum phenomena on networks, to name a few, as well as biological networks, complexity, and criticality in condensed matter. Over to you, Ginestra.
Thank you so much, yes, for the introduction. Yeah, I want to resonate with what Stefan was saying, that actually it's very interesting to see how networks are both useful to understand the real system, real physical system, like social network, the brain, and then how flexible, how this structure, how flexible they are to do distributed computation. And I've been inspired by a lot of application going from finance to neuroscience. And recently I work a lot on these generalized network structures, so multi-layer networks and simplicial complexes. And these are actually very interesting structure because they are tensorial. So we have learned how important are, this generalization, not only to graph, but to tensorial structure. And there are a lot of mathematical questions that arise from application. And I want to mention just a few. So one is the one I spoke about. So this fact that, maximum entropy ensemble, they give model given a set of constraints, but typically these models do not have an explanation for where the constraint come from. And then there is a need for a new technique to understand where this constraint comes from and potentially how do they evolve or co-evolve with the network structure. So there are kind of two classes of models in which the constraints are topological. So they, you constrain the node to have a given degree sequence or things like that. And model in which the constraint comes from feature of the node, external feature. But we know for community detection that these two actually speak together, right? And they actually also evolve in time together. And there is a need to understand where this constraint comes from, or if they are even a real fixed constraint, or they're just co-evolving. And another important question, I think, is the one of the characterization of the spectral property of network. And we have really appreciate a lot the presentation from William was really great. And recently we are working on simplicial complex spectral properties. And these are actually quite revealing because there is an entire world right there is waiting for us, in which there is not only the graph Laplacian, but there are also the higher order Laplacian, which characterize diffusion, not happening from node to node through links, but for instance, from links to triangle, and so on. So these different kind of diffusion processes can coexist in the same network, and they can give rise to different type of information at higher order, which open space for topology. Yes, I think these are the most burning question. Of course, there is the question of compressibility, information content of model, and all of that. And also, I've been working in the traditional way of message passing, but I think that graph neural network open a whole new scenario for we have been playing with this rule for message passing one by one to do analytical result for epidemic spreading or so on. But actually graph neural network have, this kind of exploring the space of possible Hamiltonian, physics would say, about the dynamics and the possible solution of algorithm.
Thank you, Ginestra. I really like the part where you compared the parts about traditional machine learning versus the modern techniques. I'll move on to Ines. Ines Chami is a star PhD student at ICME at Stanford. Her work focuses on models that can learn representations for complex relational structures. We just heard a talk from her on non-Euclidean geometry. And she also has interesting work on intersection of knowledge graphs with computer vision and NLP. Over to you, Ines.
Thank you very much for the introduction. So on my end, my work has been mostly focusing on hierarchical data because there are some nice connection with hyperbolic geometry. And so far, the problems we've been looking at are related to natural language processing. So for instance, knowledge graphs which have many latent hierarchies in them. Also parse trees. There are many applications that deal with hierarchical data in natural language processing, but something that I'm really interested in investigating in the future is anything that relates to medical applications. So one of them is medical ontologies, which also have a lot of hierarchies in them. So all those complex medical terms can be stored in hierarchies. And so using hyperbolic embeddings there could potentially have a benefit. So I'm really interested in that as future work. And also, sorry, another application is in the area of medical image segmentation. So if you think about an image of a heart, for instance, it has the heart itself, and then it has two ventricles, and within each side it has mitral and aortic valves. And so there's also a latent hierarchical structure in that type of images. So something that we're interested in exploring is using those latent hierarchical structures to do unsupervised image segmentation. So overall, I think like places where we have latent hierarchies could be interesting to explore, to leverage the benefits of hyperbolic embeddings and potentially help on medical tasks.
Thank you. That sounds really interesting. Next up, we have Phil Chodrow. Phil is currently a Hendrick Visiting Assistant Adjunct Professor in Department of Mathematics at University of California, Los Angeles. His current research interests, as we've heard recently, are on models of random graphs and hypergraphs, dynamics of adaptive networks, inference in generative network models, and techniques for clustering higher order network data. So over to you, Phil.
Hey, thanks so much for the introduction, and again for the invitation to be here today. I think there's, I mean, gosh, there's so many interesting questions that remain open about generalizations of graphs broadly construed. Some of the directions that I'm especially interested in most recently, I'd say they can divide into roughly two branches. So the first of these is on a similar theme to my talk today, and this is mathematical treatments of heterogeneous hypergraphs. So these are hypergraphs that have varying node degrees, but also varying edge sizes. And I think that there's been a lot of great work done on questions like, what's the right spectral story for hypergraphs where the edge sizes where the edges are different sizes, for example. And I think there have been some really great pieces of work on that story, but I also think that story is not over. And that there's going to be a lot more further development there that is going to relate to how to optimize with tensors of different dimensions in the same objective function that I think I'm really excited to see development there. There's going to be stories about non-backtracking operators on these heterogeneous hypergraphs, for example. And I'm really hoping that, as I mentioned in my talk, some of these stories might relate to detectability problems in graph clustering. So I would love to see development there. I'm hoping that I'll be involved in some of it, but I think there's a really fertile ground for thinking about how do we really take a principled mathematical approach to hypergraphs with heterogeneous edge sizes. I'd love to see more work there. Another area of interest for me is in connecting graph structure to dynamics on or of the relevant graphs. And I think that there's I'm actually kind of especially interested in small data on these questions. So there's a lot of really interesting graphs that come to us from researchers in social science or in animal behavior, for example, that are kind of this case where you really need to wring every little bit of statistical power out of your observations because there just aren't that many of them. And so the question of how do you apply network science techniques to support inference in these settings, especially in settings where there's a time element, the settings of your observations might change, or there are sampling biases, you only observe certain individuals, for example. How do we think in principled ways about how to process and report on those kinds of data, I think is a really rich area that I am just getting into now. So I want to be clear that this is more about my aspirations than about my achievements. But those are two branches that are going to be occupying me considerably in the coming year or two. And if anyone wants to think about them with me, then please contact me because I would love to talk with you. Thanks.
Thanks, Phil. I really hope that you get to complete all your stories and have a nice book out of it. Next up, we have Will Hamilton. Will is an assistant professor of computer science at McGill University and is a Canada CIFAR AI chair at Mila, Quebec. His research interests lie at the intersection of machine learning, network science, and natural language processing, with a current emphasis on graph representation learning, as we've seen in his talk today, and of course, graph neural networks. Over to you, Will.
Thank you very much. And thanks again for the invitation, for all the organization. It's been great. So I have a broad range of interests when it comes to kind of complex graph and network structures, and spent a lot of time working with social networks, working with biological networks. But I want to emphasize, I think, an exciting recent direction that I've been thinking a lot about. And this is problems in which the complex network or the graph structure is in some sense latent. And I think this connects to things that were discussed by Steve and others. And this is where in some sense the clean network is not given to us. So I can give two concrete examples. So one is a really interesting challenge of trying to do graph representation learning on nucleic acid data, and especially RNA data. So RNA is obviously a sequence, but some of the most important properties of RNA actually come from the secondary and tertiary structures of how the RNA kind of folds in on itself. And you can represent these things as a network or as a manifold, and it's often easiest to think about it as kind of a graph structure where we have this primary sequence, but then we also have these edges connecting nucleotides that are interacting with one another in this more complicated secondary or tertiary structure way. And what's exciting and interesting here is that given a particular RNA, there isn't one graph associated with it. There's many possible graphs. Some of them are more likely, some of them are less likely. And when you're developing learning algorithms, in some sense, the most sophisticated thing that you can do is actually trying to not just rely on some off-the-shelf guess of what the interesting graph structure is, but your algorithm needs to learn what the graph structure is. So when you're looking at this sequence of nucleotides for this RNA, how can this RNA fold? Or if a protein as well, although protein folding is a lot more computationally involved. But thinking about actually inferring the graph structure, so inferring the relationships while you're doing the learning. And I think it's a really exciting direction. So in computational biology, so I've been working a lot on RNA, but there's been some very exciting results also by Google DeepMind on proteins, right? Where we're actually trying to use things like graph neural networks and transformers to infer these latent interactions in graph structures while we're learning. And beyond computational biology, I think that the other space where this has been really exciting is in the context of, I think, knowledge graphs more generally. So for example, my group has been thinking about how agents in the context of reinforcement learning can actually infer graph structured representations of their environment, right? So things like a knowledge graph or belief graph representation of what their environment looks like. And again, what's exciting and challenging there is it's not just a static graph benchmark that we can all try to hack away at, but it's much more this complicated dynamic interaction where you're trying to solve some difficult end task. Maybe you're trying to predict whether or not RNA is going to bind with some protein. Maybe you're trying to have your reinforcement learning agent be able to solve some particular kind of puzzle. But the challenge is how you can actually leverage the inductive bias of having graph structures to improve your performance on these end goals. And I think that's been a really exciting direction. And I think I guess in some sense addressed both these data sets, but also the kind of tasks that I think are exciting, right? And I think the key idea here being the challenge of going beyond the obvious graph data sets and the obvious benchmarks are out there, and thinking about how an inductive bias towards graph structures and relational structures can enable stronger performance on a wide range of tasks, even when graphs aren't given to us.
Thank you, Will. I think after listening to all of you, we've had a very diverse panel with us. And with that, I'm going to pick on Phil because he had raised a point in his talk itself, which was also falling into one of our questions. So I would love if all of you could give your opinions on learning-based versus model-driven approaches in complex network, specifically about scalability, interpretability, and accuracy. Could you just compare the trade-offs that we have with these existing deep neural-based methods and the model-driven approaches?
Was I supposed to start?
Yes.
Okay. What have I brought upon myself?
Yeah.
So I love the diversity of this field in terms of well, we have diversity problems in other ways, but we have diversity of algorithms. You know, and I think what this really speaks to and reflects to me is that for any given task that we might want to perform, there are possibly many different motivations for doing it. And that this will, in some sense, drive what weights you place on scalability or interpretability, scalability in what direction, interpretability in what contexts, for example. So in a lot of the work that I do, I think about interpretability as given by generative models, which is a very classical and even a little old-fashioned kind of interpretability in some ways, and this reflects the kinds of interests that I have. I do some stuff that if you squint at it could be mistaken for statistics. And so in this kind of context, that kind of interpretability is of considerable interest to me and the folks that I work with. That said, I think there are really many different forms of interpretability, and the question of is this model interpretable or not is really going to depend on who is using it and for what purposes. So, you know, if you have a model that you need to deploy in a hospital, the question is, can doctors use this? You know, and that will look very different from the question of, does this model have generative foundations, because doctors don't care about generative foundations. So, you know, I think that there's a lot of cool stuff here, and I'm really excited to learn about it. And I apologize again if I annoyed anyone with my graph. Those are my thoughts.
Thank you. Anyone would like to comment on it?
Sure, I can build on that. So I sort of had a kind of it's been a long kind of journey, because my background was originally in probabilistic graphical models and sort of more explicit generative models of things, and I've been kind of a slow but now zealous convert to the more learning-based representation, learning-based things. And I just want to throw out there that some of the results that we've seen are actually kind of counterintuitive. So everything that Phil said about interpretability and sort of its importance in applications, totally agree with. But at least if we restrict ourselves to accuracy or predicted performance on some benchmark, there's really some kind of confounding or puzzling things that we're observing, like in the work I'm using graphs for zero-shot learning. There are all kinds of things that we tried to model explicitly, like edge types and disambiguations of words. And so I had the mouse example in my talk, and we tried to say, well, let's model the different word senses that WordNet gives us separately, and all of this stuff just didn't kind of matter, and sometimes seemed to actually hurt performance. So I don't have a great explanation or anything for some of this phenomena, but it's, I guess I just want to say that I'm kind of a convert now, because it's uncanny, some of the things that you would think you would have to model, but explicitly, but can actually be learned, it seems, in practice.
I think maybe if I can, I'll jump in. And I think it's kind of interesting. So Steve and I both actually knowing each other from previous lives and coming from opposite directions, right? Me coming more from starting off very much on the learning side, whereas he much more, I think, had more rules and models baked in. And I think, both of us have maybe been pulled back towards the middle, so I'll give the other perspective, which is just to say that I do agree. I think there's been an interesting trend in recent years where, on the one hand, there's been an astonishing success in terms of what we can do with learned and fully learned approaches, right? And I think, this is about graphs. I think natural language processing has been where we've seen, an extreme renaissance. And computer vision, we saw that maybe in years prior, but recently, the capability of some of these fully learned in some sense approaches on language has really started to push the boundaries of making it so that there's less and less justification maybe for having more strict model-based approaches, unless you're in cases where robustness and interpretability and of different types is paramount. But I do think that in the context of graph data, there are many instances in which the kinds of graph data sets that we work on, the kind of benchmarks that we work on, so the kind of node classification tasks, tasks where we're trying to cluster users into different communities, recommendation tasks, and so on. And I think in a lot of these cases, we actually overlook the power of more rule or model-based approaches. And I actually think that there's many cases in which our learning-based approaches are not as good as we think they are. I mean, I think knowledge-based analysis is something that's been mentioned a few times. And one of the things I find astonishing is that there are, kind of statistical rule-based approaches. So there's a bit of learning, but they're quite rule and quite model-based approaches that are quite competitive or outperform, most graph embeddings and most graph neural networks, and they're very rarely discussed or kind of cited in more of the learning-based literature. So I think I'm very bullish and very optimistic about the potential of learning-based methods, but I do also think that we have a tendency on the machine learning side to overlook the strength of more model or rule-based approaches, especially as being strong baselines. And I think there's many tasks where, frankly, they're more appropriate.
Ginestra, you also had some strong opinions about popularity of deep learning versus the existing rule-based methods or the model-based learning. Would you want to share your thoughts?
I don't know. I think I never use graph learning, so I mean I'm a newcomer in the field, but I'm applied mathematician. I care a lot about doing analytical result. Maybe not completely exact result, but good analytical result for problems, so explainability of the model and all that. But I have been very impressed by the power of machine learning technique, for instance, also for very traditional problem like the inverse Ising model, which has been a challenging problem for years, and now it is solved with neural network essentially. So yeah, but on the other side, I think there is always there is some good in having a model that is fully controlled, and I see this kind of problem in the problem of fair algorithm, right? Because a learning algorithm will learn something maybe you don't wish to learn, and then you need to correct to have a fair algorithm that doesn't have bias that are undesirable. So this is exactly the same problem of having, you want to have a model for falling body in the earth, and you want, to have gravitation which remove from, any viscosity. And this is exactly the same problem. So the best fit, the best accuracy, the model that has best accuracy maybe is not the one that you ultimately want to have. And so I think there is this trade-off between, the two that one needs to take care of.
Yeah. So I was wondering if we could just continue on this conversation before I actually move to the other question. Can we think about applications where we could use part of the deep learning or the non-interpretable methods and parts of methods where we have, say, correct guarantees and we have fair allocation? Do we have a sweet spot, or are we still in that process where we are discovering how we could combine particular things?
I'll throw out a toy idea on that front. So one thing that I work on are models of opinion dynamics, and these are mathematical models that are very, very simple parables or allegories, if you will, of how agents interacting on a graph, exchanging sentiments or ideas or opinions might eventually reach some kind of equilibrium state of polarization or of consensus or of something else. And One thing that's often really an important modeling question is, well, if two or more agents interact with each other in this way, what actually happens next? How do they update their opinions or beliefs or feelings? And so there are various choices of update function that you can make that are smooth or not smooth or stochastic or not stochastic and this kind of thing. Opinion exchange data is difficult to get, but it would be interesting to ask, well, is this actually something like a kernel that we can learn, this kind of update function? And then if we can actually get some empirical, some properly learned empirical justification for a kernel choice, can we then understand what the mathematical consequences of that learned representation might be? I think this, if you can get the data, which is difficult, but I think if the data can be gotten, this would be a pretty interesting kind of thing to do.
Anyone else? Okay, Ines, I had a question because you also had brought up the topic of using your methods for the medical domain as well. Could you also comment on the nature of interpretability if you plan to use deep learning methods on it?
Sorry, just to make sure I understand the question. Comment on the interpretability aspect of
yeah, especially when you're using for medical domain.
I see, okay. Yeah, I think that's the main, one of the main benefits of using graph-based learning methods is that you can, for instance, use dimensionality reduction to visualize the data that you're learning and try to interpret. So especially in the case of hyperbolic embeddings, we have those very nice visualization in the Poincare ball to understand the hierarchies and see if some concept get placed in the right place in the hyperbolic space, and try to visualize the notion of being a parent of something. And so, for instance, in the case of medical ontologies, that can be very useful, especially for large data sets where we can zoom in and understand whether these embeddings are qualitatively good, and then we can pair this with quantitative measures to see if the method actually learns something useful.
Thank you. That's an interesting insight. Before I move on to the more general aspect of this panel, if there are any questions the audience would like to ask, I would ask them to place it in the chat or just raise hands and somebody will let you ask the question. The reason why we organize this workshop is because we've seen that certain problems are central to several disciplines at once, while there are certain problems which require everybody to just lend in their expertise and work on one particular problem. So the glaring example of it being AlphaFold. So if people over here have had experiences working across disciplines and working across problems which have a diverse approach, could we just have what your experience have been so far, and how do you think we could have a better communication together as a community?
Maybe I'll jump in on that one. Yeah, I think it's a challenge, obviously. I think anyone who's done interdisciplinary work knows it's a challenge. I've had the good fortune to do it in a variety of contexts, so both with social scientists as well as with biological domain experts. And I think, it's in no ways a solution, but maybe to highlight one really important area that I think often leads to a lot of friction, although again, I've had a lot of success, but it is definitely an area of friction, is making sure there's an alignment of what the objectives are and kind of what measures of success are, right? And I think, quite frankly, we as machine learning researchers or network scientists, we often have very different measures of success than a sociologist or than maybe even a medical researcher, right? And I think sometimes we're more or less aligned, depending where we come from, but in extreme cases, right, it can be this mismatch between having high accuracy on a benchmark versus actually having something that's translatable into a wet lab. And I think making sure that there's communication on translation of objectives and alignment of objectives at a low level, right? And not just a high level of, oh, we want to try to solve this problem, but how are we going to ensure the translation of these prediction algorithms to something that's relevant in terms of this particular domain application? And I think that, if not dealt with upfront, can really become a major sticking point. And then maybe a slightly less interesting one, but one that's very related, right, is just an alignment of what goals look like in terms of timelines, right, and how that looks, because this is another area where there's a vast mismatch between different fields. And I think making sure there's alignment on these, they're important, but they can seem mundane, right? You say, oh, everyone's just going to do good work and it'll all work out together. But when you have machine learning researchers who are working on a 4-month research cycle and wet lab collaborators who are working on a 2-year research cycle, and they have very different meaning or different assumptions of what success looks like, that can lead to a lot of friction. So I think just having those discussions up front and making sure there's a space for the alignment and a good middle ground is pretty essential.
I'll just add to that something, actually, a conversation I had this morning with someone else highlighted for me, which is related to goals. There's a very mundane goal about publication venues as well. And a bit of a bummer is that a lot of people who might want to collaborate with machine learning researcher, for example, are going to be facing hiring and tenure committees who think that conference publications are not, in fact, publications. If you should say, oh, this appeared at a conference, they're going to say, okay, great, why didn't you publish it afterwards? So there's this kind of cultural problem around, like, okay, the publication venues that might be really well incentivized for folks in one community may not be well incentivized for folks in another. And so there's a challenging barrier that I'd love to see lowered in that way. I'm kind of in between, so I'm sort of looking on both sides, but a lot of folks are not in that position.
I mean, adding something on top of it, so I am a researcher in NLP, and I'm recently in a place where we are full with social linguists and people doing psychology. And then I come from a very computer science background. So the way I explain compositionality and the way they explain compositionality is totally different. And we just go on arguing about it. So when we are looking at targeting an audience, which is composed of people who are across different domains, are a diverse audience, how is it that you write papers for them?
Yeah, so I wanted to jump in and build on that, because one piece of advice that I would maybe add in addition to the great things that Will and Phil said is that just agreeing on that language, like before you get to writing the paper, just agreeing on or learning that language between each other's fields can be time consuming. And so in the interdisciplinary work that I've been fortunate to do, the ones that were more successful versus less successful, there's a strong correlation between how much time we spent just kind of going back and forth. And it's like, well, you said this, and I think that means this. Is that right? And doing several rounds of that, like maybe every meeting for a long period of time, really a substantial amount of time. So you know, that would be my piece of advice is to that if you want to do that interdisciplinary work, it's time well spent. It's a necessary investment. And so I don't know that I have great answers about how to do the writing beyond, hopefully at least you've learned something from that process.
Yeah. Before we have some more questions, I think we have some questions from the audience. So this is directed for Phil. Oh, wait. What are speakers' general insights about applying game theory RL on complex system and network related problems? I think he had a mention of opinion adoption, iterated prisoner dilemma and graphs. If you are in the audience, could you just come online and ask the question yourself? I may have not interpreted it correctly.
Yes, so I think it is just a general question about, like, because I see a very works in complex system regarding like large economic agents, how they interacting on the graph, and the related how the related graph structure property influence the agent's behavior, and there is some kind of phase transition property occurs. So I just wondering what's your general opinions or related direction or insights? Yeah. Yes, that's my question.
So I guess I said the thing that started this question off, but I think actually Ginestra might be a much better expert than I am on this. So I would love to hear her thoughts on this as well.
Unfortunately, I'll have to back out.
Yeah. Yeah. So yes, there is a lot of interest in game theory on networks, and of course, in generalized network structure, this is becoming even richer because both multi-layer network and simplicial complex give a much richer structure to game theory. So you don't have just a table of 2 players, for instance, in simplicial complexes, but you can have 3 players. So and this is very important, for instance, also in ecology, right? Because you can have a very different type of interaction. And yeah, personally, I work also with some people in the financial sector. For instance, if you have, this is not game theory, but if you have, you know, a different financial institution that have different type of contracts, then you will have a multi-layer perspective, you know, perspective in which two financial institution can have different contracts. And this is very important for, you know, measuring the risk for crisis in the financial sector. So yes, there are these major problems connected to big financial crisis, like the newly introduced counterparty, which clear the market. And yeah, I can I can point you a paper which I did with the Bank of England about this. Yeah, but there are a lot of problems connected to this generalized network structure, which enrich game theory and economic kind of modeling.
Yeah, thank you, Professor. I was looking forward to see these papers.
Just to add to that a little bit, one thing that I find really exciting going on from many people right now is the incorporation of data broadly construed, so incorporation broadly construed in studies of these kinds of dynamical systems on graphs and higher order structures. You know, historically, a lot of these are mathematical toys, and I'm a mathematician. I love mathematical toys. But I think more and more now we're seeing the incorporation, not just of realistic graph structures, but also of other kinds of data where we can start evaluating, you know, are these plausible mathematical toys? Do they have any kind of predictive power? What can we learn from them about real systems? And so I love the increasingly interdisciplinary and increasingly data-informed approach to these kinds of problems. I think there's so much exciting work being done there, and I think there's so much more exciting work that will happen in the future.
Thank you, Zunli, for asking that question as well. Moving on to more heading towards more of a, what do you think is the future of this field when we look it through a multidisciplinary angle? Not just the problems that you find interesting, but the ones that need urgent attention, and that I think everybody who is part of this audience wants to have a go at it some point in their life. Oh, by the time I give some time for you to think. I think there's a question from Nihal Nayak. Nihal, do you want to give it out?
Yeah, thanks for organizing this panel. So I guess this is more of a question to people who worked on both graph neural networks and hyperbolic graph networks. So I guess I want to understand why you would choose hyperbolic graph networks over graph neural networks. So what are some potential like trade-offs? I guess I'm asking this question because folks who work in graph neural networks have also started working in hyperbolic graph networks. And I guess from Will's talk, we also learned that graph neural networks have problems where across multiple layers, you cannot propagate information. So is that one of the trade-offs you'd consider? And yeah, I'd just like to know your views on that.
I can answer a bit on this one. So I think really the trade-offs for using Euclidean graph networks, which are just the standard ones, or hyperbolic models or hyperbolic graph networks really comes in the data. So depending on what data we have as input and what structure it has, we may choose one or the other. So especially for hyperbolic embeddings, as I mentioned in the talk, there really, we see some benefits when the underlying data has a hierarchical structure. So we have some type of tree-like patterns in the data, and that's really where we can see benefits from using a hyperbolic embedding space. So that may be a potential way to use a hyperbolic graph neural network compared to standard graph neural networks. And then this comes at the cost of having to define all the neural network operations in a hyperbolic space. So these spaces are not Euclidean spaces, and we can't do the standard mathematical operations that we're used to, like matrix vector multiplications or additions. So when we want to generalize a model to the hyperbolic space, we have also to come up with a principled way to generalize these operations, which can be a bit harder than directly applying an existing method. So those are trade-offs to consider. But if the data is really tree-like, then there's definitely some potential benefits in using hyperbolic embedding spaces.
Thanks, Ines. Nihal, do you have anything more to ask?
I guess follow-up would be like more in terms of what direction people are finding promising, whether it is trying to improve graph neural networks in the Euclidean space or trying to improve hyperbolic. So I'm not sure if like which ones are more promising over the other. I understand that hyperbolic graph neural networks do require hierarchy, but in places where you don't have hierarchy, would I'm just guessing graph neural networks would be the de facto, right?
Yeah, I think so. And I think the developments are in both areas. So there's one thread of research that investigates how to apply some operations in hyperbolic space and how to develop models for that space specifically. And there are other directions that develop graph neural networks. And I think because of the volume of people that work in GNN versus hyperbolic space, then obviously the advancements are bigger in the Euclidean space, but the hyperbolic folks are trying to like catch up and build their equivalent models in these new geometries.
Okay, thank you, Ines, and thank you, Nihal, for bringing in that perspective. Okay, moving back, because we have just about 5 minutes to go. What do you think people should be looking at when they want to approach this particular field, and what do you think are the most promising problems to look at for?
It's a tough question.
I think they're being modest, but I just want to give a shout out to Will and Ines and on the graph neural network side. I mean, what they've already talked about of, what are the fundamental limits of the representation power and what geometry should be using? Those are huge questions.
Yeah, I think, and what I was going to say to build on that is I think, there's two places to look, right? There's what are the theoretical challenges and what are the real world challenges, right? And in both of those spaces, there's a lot of things to sink your teeth into, right? I think I talked about, what are the limits of the current GNN paradigm? And I think what's the limits of also learning in Euclidean spaces is another fact. And thinking about how we can break those barriers is a really important one. And I think also mentioned by Phil is working with hypergraphs, right? There's all these important questions of pushing the limit in terms of the theoretical capacity of these techniques. But then on the other side, I think it's really important to think about what are places where these techniques can have impact, right? So computational drug design is one that I've mentioned a couple times. And I think, that's a place where these network analysis and graph learning techniques can really have huge impact. And so that's maybe an important thing to look into. It depends very much what perspective you're coming from.
Ginestra?
Yes, it's difficult, to predict what will be leading to the next big step ahead. I think in any case, it would be very important, to have quite some attention to these simplicial complexes and hypergraph, and then if I need to bet, for the mathematical theory which I prefer, I've been working a lot now on topology, and it's really beautiful, and also geometry. So I really like this importance of hyperbolic geometry also for learning. But I think, my belief is that ultimately it's information theory only that practically will it is so such an abstract theory that I think it's the one that I would think it's the more that is the one that has more promise for getting some understanding about learning and network and this graph object.
Okay. Thank you. And before I move on to the official closing section of this workshop, is there any questions with the panelists would like to ask the other panelists?
Yeah, I have a question for Ines. So she said that this tree-like structure are the one that are best, the best, the ideal setup for this hyperbolic graph. But in graph there has been a lot of speaking about hyperbolicity of graph and this notion of delta hyperbolicity. So which has been claimed that many networks actually are delta hyperbolic, so they are kind of fat type of graph. So is there, but there is very difficult to say, delta hyperbolic, what does it mean respect to the diameter of the network? And so do you have any clue? Are you thinking about this topic, or when does it start to fail? You say you can learn the curvature, but I don't know.
So that's a really good point. So actually I should have mentioned that in the talk, but the delta hyperbolicity is an excellent measure to identify graphs that will be good candidates for the hyperbolic space. So delta hyperbolicity 0 is just a tree, and there's some result by Sarkar. It's a theory paper that shows that trees can be mapped to the hyperbolic space with 0 distortion. So we can have a perfect mapping and preserve all the distances. And as we increase the delta, then the benefit are getting smaller and smaller. So that's what we showed actually in one previous paper, trying different ranges of data sets from trees to data sets that weren't tree-like at all. And we saw that the gap between Euclidean and hyperbolics were getting smaller and smaller. Obviously, it's not a perfect measure, and we can't say exactly how it's gonna be, but we're trying to find those type of metrics beforehand to identify good candidates for the hyperbolic space.
Thanks.
Thanks for the question.
Are we expecting any more questions, or should I just hand over to Deepak?
No questions, but I'd like to say thanks to the organizers as well as the other panelists for the opportunity to learn about some very interesting things from them, both from their talks and the panel. It's been a great experience for me, and I'm very grateful.
Likewise, it's been great to see and meet you, and thank you very much to the organizers.
Thank you so much.
Thank you.